Welcome to The Explainer. Today, we're taking a wild journey from the invisible, honestly kind of perplexing world of quantum physics straight to something deeply personal, your healthcare and your privacy. I know, it sounds a lot like science fiction, but trust me, the foundational science, it's already here.
So, here's our roadmap for today. We're going to cover the quantum revolution, the loss of determinism, mastering quantum entanglement, quantum healthcare innovations, and finally, protecting our quantum data. Let's just dive right in.
Section 1. The Quantum Revolution.
Okay, so this is literally one of the most famous debates in scientific history. Albert Einstein famously declared, "God does not play dice," to which Niels Bohr shot back, "Einstein, stop telling God what to do." This brilliant little exchange perfectly captures the massive philosophical clash that birthed the quantum revolution way back at the 1927 Solvay conference. You see, Einstein, as brilliant as he was deeply unsettled by the idea that quantum mechanics fundamentally relies on uncertainty.
To see why, just look at this contrast. In classical physics, think Isaac Newton, the universe is entirely deterministic and relies on standard real numbers. But quantum physics, it completely tosses that out the window. It uses linear equations, relies entirely on probabilities, and actually requires complex numbers involving the square root of -1. It is just a completely different mathematical reality.
And because the math is linear, we get these incredibly strange physical realities, like superposition. That's when a quantum object exists in two mutually incompatible states at exactly the same time. To kind of wrap your head around that, imagine a light bulb that is somehow both fully on and fully off at the exact same instant. It totally defies our everyday logic, but in the quantum world, that's just a perfectly valid physical state.
Which brings us to Section 2, the loss of determinism. Okay, so let's visualize this. Consider sending a beam of completely identical photons through a polarizer that is aligned perfectly with their path. Because the light is polarized perfectly in the x direction, every single photon passes right through, totally predictably. Classical physics handles this without breaking a sweat.
But watch what happens when that exact same light hits the polarizer at an angle. Suddenly, some photons pass right through, while others get absorbed. Now keep in mind, every single photon in this beam is fundamentally identical, yet their individual fates end up being totally different. This is exactly where classical physics just completely breaks down.
So what does this all mean? Well, determinism is lost. We can only predict probabilities. The math can absolutely tell us the overall fraction of photons that will pass through, but literally no one can predict the fate of one individual photon. And here's the crazy part. This reliance on probability isn't just theory. It's the actual engine powering all modern quantum technology.
Let's look at how we're using that in Section 3, Mastering Quantum Entanglement.
So entanglement basically links particles so deeply that their individual realities vanish. You have to treat the whole system as a single entity. Enter something called the W state. This is a massive multi-photon entanglement that is so incredibly complex, scientists have actually struggled for decades to reliably measure it in the lab. The progress here has been a seriously long time coming. First, scientists cracked a simpler form of entanglement called the GHZ state. Then, 25 long years passed. The W state remains this total unsolved puzzle. But finally, researchers from Kyoto and Hiroshima universities cracked it. By using a really clever mathematical property called cyclic shift symmetry, they managed to build an optical circuit that reads a 3-photon W state in a single shot.
And this breakthrough is an absolute game changer. It unlocks the potential for quantum teleportation. And no, not beaming up humans like in Star Trek, but transferring delicate information instantly across massive distances. It pushes forward faster quantum communication and scalable measurement-based quantum computing. We are quite literally laying down the plumbing for the future quantum internet.
So how does this affect you? Section 4, Quantum Healthcare Innovations.
Because these new quantum sensors can measure unimaginably tiny changes in magnetic fields, the medical applications we're looking at are just staggering. We are talking about wearable brain scanners that can track individual neurons firing to diagnose things like epilepsy and autism, cardiac monitors tracking minute heart fluctuations, nanodiamond blood tests for rapid infectious disease screening, and get this, single-photon cameras that can literally see right through your skin to monitor blood flow in your brain.
But as miraculous as these tools are, they collect something completely unprecedented, which we call neurodata. This isn't just a standard X-ray of a broken bone. These sensors are actually capturing the highly sensitive, magnetic echoes of your brain patterns, your emotions, and your neural activity.
Which leads us to our final and arguably most important part, Section 5, protecting our quantum data.
We really have to ask ourselves a profound question here. What actually happens when a machine can read your individual neurons? I mean, what are the real-world risks when a wearable device can detect the subtlest magnetic fields of your brain? If this level of intimate data falls into the wrong hands, it opens up the honestly terrifying possibility of neurodiscrimination. Imagine being judged by an employer or a health insurer based purely on the subconscious wiring of your brain.
So, to prevent that kind of misuse, regulatory bodies like the UK's ICO are pushing a really strict privacy by design approach. This involves a few key steps. First, conducting rigorous data protection impact assessments or DPIAs before rolling anything out. Second, enforcing strict data minimization. And third, ensuring the early pseudonymization of research data, which basically means stripping away all your identifying details before anyone ever analyzes it.
The core philosophy that regulators want the medical industry to adopt is beautifully simple. More detail does not always mean better. Only collect what is strictly clinically necessary. Just because these quantum sensors can collect massive amounts of your intimate neural data doesn't mean they actually should. Data minimization is definitely our strongest defense against privacy breaches in this new age.
As we stand on the brink of this incredible quantum era, leaping all the way from Einstein's philosophical debates to actual machines that can read our brainwaves, we have to wonder, are our current privacy laws truly prepared to protect the inner workings of our own minds? It's a question we are all going to have to answer, and very soon. Thanks so much for joining me on this explainer. Keep asking those big questions, and I'll catch you next time.